All right, so you'll have the joy of doing homework problems like this, so we don't need to spend all of our time. But if you wanted me to do any parts of that problem, let me know. Okay. Basically, I did want to say if the easiest thing to do for part D is plug in the velocity value you found for part C and just do 1/2 mv squared for the kinetic energy. And that was easier than trying to do all this long business. Yeah. Okay, so where were we? Forces, moving on, energies, that one. Okay, so we already talked about the Galileo, and we've talked about this as kind of like a phasor diagram. And we talked about the position one, where your horizontal position is just the shadow of that amplitude vector on the x-axis, and that was pretty understandable. For velocity, you can think of the motion of this object in circular motion having a velocity vector, and that velocity vector is constant because it's like uniform circular motion. So that velocity vector is going to stay the same length at all points in time, but if you take the shadow of that down on the x-axis, that will change length as the velocity vector moves around. So this is your v of t, that's your velocity vector as it changes with time, and then that's your maximum velocity vector, which is constant throughout time. And then last but not least, acceleration. Your acceleration vector points towards the center. That's your centripetal acceleration. So this vector is going to be constant as a function of time as you're rotating. But again, the shadow of that vector on the x-axis will change as your object rotates. So your x-axis is your a, your acceleration is a function of time, and this vector on the hypotenuse is your maximum amplitude acceleration, omega squared times a. So that's basically the phasors for all position, velocity, and acceleration. So this is mostly just for your own conceptual understanding. There's not really going to be any questions pertaining to these pictures, but if you have any questions, let me know before I move on. Okay, pendulum. We've got what we call this, right? We've got a simple pendulum, which is making a lot of assumptions. And then we have a physical pendulum, which is where we try and treat it like a real system as closely as possible. And so you're going to hear or see this in a lot of problems where they say, solve this like a simple pendulum, and then solve it like a physical pendulum. Okay? And so I'm going to explain both of these, and they both have some approximations to them to make the math a little bit better. And we'll talk about what those are. So the simple pendulum is where you idealize the system so that the mass that's swinging is like, you can treat it like a point mass, and you treat it like all the mass is located right here, and the string is massless. Non-stretching string, of course. The first approximation we're going to make, well, I guess these are some approximations, right? That the mass is all located right here. So the second approximation is using the small angle identity. And the small angle identity says that for small angles, sine theta is close to theta. And as long as it depends on what your accuracy needs to be, but that typically is less than 15 degrees. That's sort of the rule of thumb for using the small angle approximation. So if you look at the restoring force, in this case, it's gravity. And at this point in time, as the pendulum's coming back towards equilibrium, the force that's pulling it back is this vector component of gravity, mg sine theta. So that's the force that's the sort of our springiness force, minus mg sine theta, and using the small angle approximation, we can just call it mg theta. Now, the secant, if you remember, that was sort of like the distance along an arc length. And we learned this in 221, So the arc length, I'll draw this here. So we called secant back in 221 S, and then this is theta. And then for the sake of matching my slides up there, the radius I'm going to call L, since the radius in this case is the length of the string, L. So our secant length was defined as, how did we define that? L times theta. So rearranging that for theta, we've got, oh, and I called it X up here. X equals S. So rearranging that, we have theta is equal to X over L. So I'll replace theta with X over L in our force equation. Now, since this is a restoring force, we can equate it to the spring force. So that's the next step. We know that our spring force equation was minus kx. And now this restoring force has the form of minus stuff times x. So what was a spring constant when we had a spring, now our springiness term, sort of the constants wrapped up in the pendulum itself, is mg over L. That's sort of, if you think of a spring, the k value is bigger if it's harder to pull the spring. So the stiffer the spring, the bigger the k value. For our pendulum, the bigger this value, mg over L, the harder it is for that pendulum to swing out. The more it's going to want to stay close to equilibrium. Yeah, Ian?
So the x in that case is just along that arc?
Yeah, so it's not really a straight line position, it's the arc distance traveled, yeah. But I just used x to sort of make it clear how we equated it to the spring constant. So just what we're saying here is that the springiness term the spring constant term for a pendulum is mg over L. So if your mass is bigger, it's going to want to stay closer to equilibrium. So that's like having a bigger spring constant. If the length is longer, so bigger L, it's going to stretch out further, and so then you're going to have a more springy pendulum. Okay, so that's matching our expectations.
Have you ever had problems that have like a pendulum angle of greater than 15 degrees where we can't make that approximation?
We won't, but you might in the real world.
Okay.
I actually worked in a research lab, probably told this story before, but I worked in a research lab studying balance, and I was working with a grad student, and he was a mechanical engineer. And we treated the human body like an inverted pendulum, and that simplifies the math. And he was trying to use a small angle approximation. Actually, he did in all these calculations. And I said, I've seen people swaying bigger than 15 degrees. I don't think you can do that. And he's like, no, it's fine. Don't worry about it. And I was like, well, I've got nothing better to do. I'm going to rerun all your calculations using sine theta instead of theta. Because it really wasn't that big of a deal. You got MATLAB, so you just change it in your code. And it turns out that it caused about a 7% error in his data, which was significant. And so, booyah, I won. No, it just goes to show that it depends on the situation and what your specs are, and you can't always assume that you can use a small angle approximation. And since it's really not that hard to use sine instead of theta, But for the sake of the simple pendulum and for simplified physics, we'll just use the small angle approximation today. But as good engineers, you always, that's why you're in physics, is so that you know where these equations came from and you can go back to the source material if need be. Okay. So I'm going to take what was in our angular frequency definition of k over square root of k over m. I'm going to replace k with mg over L, and things cancel. So for a simple pendulum, our angular frequency is now the square root of g over L.
So in the restorative force, it was saying that it was a negative mg over L?
Yeah, because just so I could easily equate it to my spring force equation, which was minus kx, I drew my arrow to the left so that my mg would be a negative, in the negative direction. I just did that so it was really easy to see how the terms matched up to the spring force equation.
Got it.
Yeah. Okay, so the take-home message then is our angular frequency is g over L. And then our period, plugging in our new omega value, we can write our period as 2 pi the square root of L over G. And so that's a surprising result. Mass didn't matter, right, because it canceled. The only thing that mattered was the length and what planet you're on. So when you make some simplifications, you see that really the driving forces of penduli, is the length and gravity. So that should be something to think about, I guess. I think about that sometimes when I'm on the swings with my daughter. Okay, now physical pendulum. This is more like a real system. So we're going to make a few less approximations. So we're assuming that the whole rotation arm has mass. So this is like springs or strings with mass. Or instead of rotating a string with a bob on the end, maybe you're rotating an object that has more of a solid body throughout the whole thing. There's a lot of things you can rotate that can find pendulums in the real world. Let's see. I don't know. Like your coat, for example. Like my whole coat, the whole thing has mass, but I can turn it into a pendulum. All right. So I can't ignore all the mass that's right here and just say all the mass is located down here, because that's not accurate. So this is more of a physical pendulum kind of situation. Or rotating your golf club, or your grandfather clock has that big metal disc and then a metal rod. You can't ignore the mass of the rod. So those are examples of physical pendulum. So I think all of you guys haven't really done much with torque because we've had to cut it out of 221 and 222 for time. This isn't critical to problem solving, and it's just critical to an explanation, so you can kind of just accept this as is. But it turns out that torque, which is an angular version of force, it's basically our angular version of force, is equal to the inertia times angular acceleration. Okay, so if I had had a lot of time in 221, you would have learned that, but I think this last term I didn't, and I'm not sure about fall. Did we get to that in fall term? For those of you who are with me, fall term? No, okay. Okay, so what we do with torque is we can, this is sort of like F equals ma, and then you write down all the forces on your free body diagram. So this is like our ma, F equals ma. And now this is all the forces on our free body diagram, except torques. In this case, torque is force times the distance from the rotation axis. So for a pendulum, the force is gravity, right? And the distance from your rotation axis is the distance from your center of mass to the pivot, which in this picture is little d. So the force, the restoring force again was mg sine theta. So that's our force multiplied by our distance. So again, this isn't critical for your lives, but you would have learned this if we'd gotten to it in torque. But some of torque, let's see. So this is what it resembles, right? F equals ma equals minus all the forces, F1 or plus F1 plus F2 on your free body diagram. So for a sum of torques, it always equals I times alpha, and then you add up all your torques, which is force times distance. So that's where this is coming from. We only had that one force, mg sine theta, due to gravity, and the distance from the pivot is little d. So that's what this is. And then again, we make the small angle approximation. So it just becomes minus mgd theta. And in this case, I solved for the angular acceleration from over here, alpha. And so what I got was mgd theta over I. So that's the side that makes sense. And then I just reminded you that angular acceleration is the second derivative of angular position. The reason I did that is to, let's see, where's that coming from? Minus k over m. Let's see, what was our A of t equation? A of t was minus omega squared A cosine of stuff. And x of t was A cosine of stuff. So this is the same as minus omega squared times x of t. Oh yeah, okay, so this is the same as minus k over m quantity squared x of t. So minus k over m x of t. Okay. Looks like I needed to do some notes for myself on here to figure out where this came from. Okay, so what I was trying to do is trying to find a relationship between common terms here. So when we did inertia back in 221, I said that was sort of like your angular version of mass, except with rotating objects, you have to take into account not just the mass, but how it's being rotated. So what I was looking for was an equation that, an acceleration equation that had a mass thing on the bottom. So this term had a mass thing on the bottom, if I do some funky algebra like I did over there. And then on top, now our k term that looks similar for the physical pendulum our k spring term looks like whatever's on top here matching with this equation over here. So in this case, that's the mgd that's similar. Okay, so I just said k over m is similar to mgd over I. So I'm going to use that on the next slide. Okay, so we already defined omega as the square root of k over m. So now for a physical pendulum, we can use the square root of mgd over I for our angular frequency. So I is going to be the inertia of whatever shape you have, and d will be the distance from the pivot to the center of mass of that shape.
And so you just brought over the second m to make it like m squared.
No, I didn't bring over the other m at all. This is, so omega, we said before that omega is defined as the square root of k over m. So if I just take the square root of this side and the square root of this side, then this would all be equal to omega.
Oh, I see what you're
Yeah. And then T would be 2 pi the square root of I over mgd. So the reason I keep solving for period, that's like a really commonly asked question about a pendulum. You see a pendulum, you go, oh, what's the period of that pendulum? Well, this is how you could find out. Okay, so as long as whatever object your physical pendulum is made out of, you can look up the inertia for in a table. So table 9.2 in your textbook has all these different objects being rotated. Most of them don't look like they'd make very good pendulum. Pendulum. But pendula? Some of them would. So in this picture right here, they give you an inertia equation for a rod being rotated on one end. So that's cool. We don't have to do anything funky there. If you had a rod being rotated, you could just use that inertia equation, 1/3 ml squared, up in here. Sometimes we're not so lucky though. Let's do sort of a simplified grandfather clock where you've got a big heavy disc being swung on a string, for example. So in that case, you have to use the parallel axis theorem.
Which, by the way, wasn't on that final where you promised us most of the videos.
Oh, yeah, sometimes that happens when I look at what I need to test you on and what isn't quite as important to test you on. Okay, so there's a disc being rotated, and the length of the string is given, and the radius of your disc is given. And you want to figure out the period of this physical pendulum. So we have to remember the parallel axis theorem. It says the inertia that we use is going to be the inertia of the center of mass of that object plus md squared. So for this case, the inertia of the center of mass for a disk is 1/2 mr squared. And now what is my d? What's the distance from the center of mass to the pivot?
L plus R.
Yeah. So from there to there. So that's kind of yucky, but that would be the inertia you'd have to use in your period equation. So your period would be 2 pi the square root of all that business. I'm going to pull the m out. Divided by mg, and then d was L plus R again. Am I? Yeah. Thank you. So you can simplify. You can see mass cancels. So mass shows up in all inertia equations. So even for the physical pendulum, mass doesn't matter.
Sorry, I missed that. What
Yeah,
is the
Jacob.
comp? You call it comp?
Center of mass.
Oh, center of mass. Okay.
Good question.
And that's just a formula you looked up in the book.
This part? Yeah, this is the inertia of a disk. So depending on your shape, that's going to alter this calculation. Yeah. So for example, so this would be your T physical. If you decided to treat this system like a simple pendulum, let's see how different your equation would be. It would just be 2 pi L over G. If you wanted to, you could say, the length is, if you're treating it like a point mass, then the length is still L plus R, which I think would probably be more accurate. So if you plug in numbers, you can see that as long as your R is small, these are going to be pretty close to each other. But as your R gets bigger, then your simplification is going to be less and less accurate. All right, so that's really all I have to say about pendulum, and then we've got some problems we can work on. Where are we for time? It's almost 9 o'clock. So I think we're gonna skip our bonus content tonight. I usually end up having to do that. Our bonus content is damped oscillators. So this, just to be very brief, instead of just having a restoring force, the spring force, you'd have a damping force, like friction. And your equation has not only your cosine term, that's the oscillating part, but it's got an exponential term because that oscillation is going to decay. And it's actually quite beautiful how you can see the cosine function and the exponential decay. That's the envelope of your function, is the a times e to the stuff. That's defining that exponential decay. I think it's a really beautiful calculation, but the kind of questions you can ask are pretty simple at this level. So it doesn't really, there's not a whole lot of complicated questions that involve the damped oscillator. But as you guys know from circuits and stuff, damped oscillators come up a whole lot.
A lot of questions you can ask if you put circuits in it.
Yeah. And so that's one thing I'm considering right now with my 222 class is I have time. I could probably introduce the RL circuit and do some really nice damped oscillations. Yeah. But for a pendulum, you know, this pretty much all they ask is they say the critically damped case, these are the values, solve for your frequency. So it's just kind of plug and chug kind of problems, which are pretty boring. So, but if you're interested, not critically damped, there's 3 cases if you've never seen a damped oscillator before. The critically damped sounds like it's the interesting case, but it's not. I always get mixed up. So critically damped, the system just returns to equilibrium without ever oscillating. So it just kind of goes, and it's done. It's damped. I mean, that's the point. You want to damp out your frequency, then it's damped. It didn't oscillate. Overdamped is, again, it's not going to oscillate. It just decays to 0. And then underdamped is the one where you get the pretty curves. So you didn't have enough damping. That allows the system to oscillate for a while. And so if you're just interested in the terminology, which will show up in a circuits class later on, underdamped is the interesting case. Probably don't really want that in your circuit, but as a physicist, that's the one that I find most interesting. Right. Okay, so we won't do the problem. You had one homework problem involving the damped oscillator, and so you can skip it if you want. If you want to do it, you can do it, but I won't be grading it. Okay, so we can work on the pendulum problems that are in the worksheet, or we can start the lab. Who votes to do more problem solving? Okay, so everybody's voting to do the lab.
Yeah.
All right, let's take a 5-minute break because I got to print the lab.